Everyone has joined in. Can I start? Guys, you can hear me? Okay. Someone left. Okay. Good morning. Okay, how many are left now? 1, 2, 3, 4, 5, 6, 6. Totally 11 should be there, no? Four more people. Total 10. Okay, by the way, you all went over whatever I had done yesterday. You all check the website and all. You all can chat with me. You all, okay. So go on to that web, check it out. Okay, for the practicals was the solely source of conducting the practicals. I know that there is no way of keeping the components and all, but at least you will be able to change the values. That's the only thing we can do as of now. Okay. Once the COVID lockdown gets over, then we can basically do it on a physical breadboard. But otherwise, we can only change the values. You cannot do anything new. You cannot experiment more. But as I told you, like last time, if you want, you could just purchase a breadboard, okay, and those components hardly cost around some 5 or 6 rupees, and you can play around with it. Even for an adapter, you can use your normal mobile charger only and get the 5 volt or 6 volt. Okay, so coming back, today we will basically go for our full logic gates. I will just share you my screen. Okay, can you all see my screen? No? Okay, all right. Cool. Okay. So I'm lowering this, putting the power presentation on. All right. Okay, I hope you all can see this. Please just one of you all come out from your mic and just say yes, so I'm confirmed, because right now it's on full screen.
Yes, sir.
Okay. If in case the screen goes off, just come out from your mic and just tell me, because I'll not be able to see you all if you all are there or not there. Okay.
Yes, sir.
Cool. Okay. So right now we are basically going to go for logic gates. Now, what are the chapter goals? First is to identify the basic gates and describe the behavior of each. That means we will see the different gates which are available, like AND gate, OR gate, XOR gate, okay, NOT gate, and we'll see how they work, how they behave, okay, given the different input signals, what output we receive. The second thing is, the goals of it is to implement using transistors. That means how can we use transistors and implement these gates, because finally these gates or these ICs, AND gate and OR gate ICs, they are made up of transistors only, right? So how we can use transistors and make up these gates. If in case any of you all is having a doubt, you can just interrupt me in between only, come out from your mic, okay, put your mic on and directly interrupt me, okay, no problem. Then how to combine basic gates into circuits. That means how you can use these gates, okay, for a 1 and 0, for whatever output, to make them and to push them into circuits, so that we can use them for useful tasks. Say if I get an input of 0 and I get another input of 1, and I want an output of 0. So what I'll basically use, I'll use a normal AND gate. So 0 and 1 gives us what? 0. So that is basically a AND gate. So that 0 output, I can use it for some other circuit, okay, to basically give me a yes or a no, or to turn on or to turn off. So we can use this for our circuits. Then describe the behavior of a gate or circuit using Boolean expressions, okay, truth tables and logic diagrams. Boolean expressions are all your, we will come to that. Your truth tables, Boolean, logic diagrams are basically all explained through your OR gate and AND gate, how they behave. So there is something known as truth tables, okay, and your logic diagrams, whether it's going to be basically a 0, it's going to be basically a 1. Your Boolean expressions is basically your Boolean algebra. Say you basically want, if you want to know, there are two inputs, A into B, okay, plus B into C. So how to solve it, what you will get, okay. So that is your Boolean expressions. What output will you get from them. Okay, then compare and contrast a half adder, full adder. Okay, now what do you mean to say by adders? Say you have 0 and 0. Say 0 plus 0 is what? 0. 0 plus 1 is what? 1. 1 plus 1 is what? 1. If it is an OR gate, this I'm telling you, if it's an OR gate, 1 plus 1 is what? 1. But if it is an XOR gate, what we get? 1 plus 1 gives us basically 0. But we can have a carry forward. Okay, so we can get what? 1 and 0. So the carry is 1 and 0 is your answer. So how we can use full adder to add on? And describe how a multiplexer works. As I told you, what's a multiplexer? You can have just 3 pins and you can have as many outputs as you want. So that's a multiplexer. Demultiplexer is the opposite of a multiplexer. Explain how an SR latch operates. Okay, so this will basically include all your flip-flops, everything. Describe the characteristics of 4 generations of integrated circuits. This will come later on. Now, computers and electricity, gate and circuit. Now, as it is seen, a device that performs a basic operation on electrical signals. Okay, gate, if you might have seen your transistors and all, it is an initial signal given to a transistor. Okay, when the gate signal is given, the transistor basically turns on. When the gate signal is not there, your transistor basically turns off. So it basically performs a basic operation on electrical signals, so as to turn on or turn off. Circuits, gates combine to perform more complicated tasks. That means more gates are combined together to perform more complicated tasks. So if there are more and more BJTs or transistors in the circuit, this is just the normal. Computers and electricity. Okay, how do we describe the behavior of gates and circuits? Okay, first is Boolean expressions, logic diagrams, and truth tables. As seen, Boolean expression uses Boolean algebra, a mathematical notation for expressing two-valued logic. Okay, so basically Boolean expression is what? You have, say, 2 inputs. It could even be 3 inputs. It could be 5 inputs. Okay, like we have A, B, or A, B, C, A, B, D, and the output is Y. For example, say we have an AND gate. We have 0 and 0. So 0 is A, 0 is B. Output of that is what? 0, Y. Okay. What do you mean to say by Boolean expressions? Say if it is a big expression, say A plus B close bracket into A into B close bracket, what is the answer? Okay. So we have a set of expressions where we want to basically get a fixed answer. What answers can it possibly have? So we can use Boolean expressions. Boolean algebra is another way of having, say you have A plus B plus C can even be written as, okay, your even A plus bracket B plus C close bracket. So we can basically put it in various mathematical forms and also keep it. Then your logic diagrams, okay, it is the graphical representation of the circuit. Okay, truth tables is basically that A, B, and 0. We'll come to that also. So there are 6 types of gates. First is the NOT gate, what we discussed yesterday, AND gate, OR gate, XOR gate, NAND, and NOR. NOT gate is what? It's just the inverse. So if you give an input of 1, you get an output of 0. So if you give an input of 0, you will get an output of 1. So if you give 1, you will get 0. If you give 0, you will get 1. So that's a NOT gate. It's just an inverse gate. There are only 2, 0 and 1 in binary. So it will give you basically the opposite. AND gate is what? It's a multiplication operator. It uses a multiplication operator. So if you have 2 inputs, A and B, okay, you have A and B. Say A is basically 0 and B is 0. 0 into 0 is what? 0. Okay, then again 0 and 1. say A is now 0, B is 1. 0 into 1 is what? 0. Now you say you have A and B both as 1. 1 into 1 is what? 1. So you have an AND gate. Same way OR is addition. XOR as I told you, 1 minute. XOR as I told you, okay, it's an exclusive OR gate. Okay, we'll come to that in detail. NAND, and then we have NOR. Okay, so we'll go for the NOT gate first. If you all are having any doubt, please interrupt me. I hope everyone is clear. Please just reply me on audio. Till here, everything is clear?
Yes, sir.
Cool. Now we have the NOT gate. Okay, as I told you, it's an inverse gate. A NOT gate accepts one input signal, that is either it could be 0 or 1, and returns the opposite signal as output. That means, as I told you, if it is 0, it becomes 1. If it's 1, it becomes 0. Your Boolean expression here, okay, here is where it shows Boolean expression, logic diagram or symbol, and truth table. So your Boolean expression shows x equals to a dash. X equals to a dash. So the a dash, the dash which is there, basically represents, you can even keep it as a and you can have a dash on top. Okay, even that is basically known as inverse. You could even have that small comma which you see on top. Okay, that is also denotes as inversion. You can even have a bar there instead of that. So even that is another way of expressing, which is totally correct. There's no problem. The logic diagram is, the logic diagram signal symbol which you can see is, you have a NOT gate. It is just in the form of a diode only, except for that dash, what is there, a small 0 is put. Okay, that circle or that 0 what you can see which is there represents the inversion. So if in case A is 0, you get the output as 1. If A is 1, you get the output of 0. So if you come back to the Boolean expression, you can see X is basically the output. X is the output. A is the input. So your output is equals to the opposite of your input. That is A. That's why that dash. Okay. I would recommend, guys, instead of putting this this small dot, what you can see here, or comma, you represent it with a dash, which is on top. I think this will be much better. Okay. So you have A. Okay. Your input is now 0. So when your input is 0, what you will get your output as 1. When your input is 1, you will get your output as 0. So this is basically your NOT gate. So when they tell you to explain NOT gate for the exam, you have to explain it in this way. First, write your Boolean expression, logic diagram symbol, and truth table. See, your output you can call your output as A, B. You can call your output as X, Y, Z, whatever. Okay. Your inputs will be A, B, C, D. Okay. You can name this character as anything, whatever you want. You could name it as X, you could name it as Y, you could name it as Z. Okay, as long as it is correct. Your nomenclature is correct and they don't match with the input signal. They should not match with the input signals. That means if I wrote A as input here, that's my pointer gone. Okay, so if I took A as input here, I cannot take the output as A. Okay, it would be basically X, Y, Z, any other character. Right. We'll go to the next. Till here, everyone is clear?
Yes, sir.
Now you have your AND gate. An AND gate accepts two input signals. Now, obviously, you'll say, sir, for the NOT gate, it's only basically one signal. Obviously, it will be one signal because it's the inversion. Okay. For an AND gate, you require two people, right? We require two people because it's a multiplication operator. It will multiply with whom? So A will be multiplied with whom? B. Okay. So it requires two and more. So we have A into B. Okay. An AND gate accepts two input signals. It's not only two input, it could be two input signals and more. Okay. So you can just remember that it's two input signals and more. So it could be A, B, C, D, E, F into whatever. If both are 1, then the output is 1. Otherwise, the output is 0. So the Boolean expression is X. X is the output. You could even name it as Y. Okay. Equals to A into B. Equals to A into B. Logic diagram symbol. So this is basically a Boolean expression, which is this. This dot represents your multiplication operator. Logic diagram symbol is this, AB. So it is a dash here and a slight round. Okay, and your output is X. Truth table. As I told you, you have two input signals. Okay, so if you have two input signals, you basically have A and you have B. So A, two zeros, okay, and then 1 1. Same way B, 0 1 0 1. So you start off from here 0 1 0 1, then you go 0 0 1 1, and then if there are three A, B, and C, then it would be 0 1 0 1 0 1 0 1 0 1 till down. Okay, it would be 0 0 1 1, then again 0 0 1 1, and then here it would be 0 0 0 0 1 1 1 1. Everyone clear with this? Please confirm me. If you are not clear, I'll explain it again.
Clear, sir.
Okay. Now your output. Since we are only considering only two input signals, okay, we can see the truth table which is here only. 0 into 0. So 0 into 0 gives us what? 0. 0 into 1 gives us what? 0. 1 into 0 gives us what? 0. 1 into 1 gives us 1. So all the outputs are 0 except for 1 into 1, which gives us 1. So this is your AND gate. Remember, AND gate, the operator is a multiplier. Then we come for the OR gate. Now in the same way how we have a multiplication operator, we even have an addition operator. An OR gate accepts two input signals and more. It's always and more. So your Boolean expression here is X equals to A plus B. So this is known as your Boolean expression. Your logic diagram signal will be A, B, and your OR gate, which is your OR gate, and your output is X. Now your truth table here has A, B, and X. So 0 plus 0, 0, 0 plus 1, 1, 1 plus 0, 1, and 1 plus 1 is 1. Okay, so this is your OR gate. Then comes your exclusive OR gate. See, your OR gate is even known as XOR, okay, but sometimes it can even be written as EXOR. You should not get confused. Both are the same. XOR and XOR are the same. So XOR and EXOR, if it's written, you have to understand it is XOR gate only. So here also we have your Boolean expression as X equals to A plus B. But now you have to see your Boolean expression here changes. You can see the operator. It is basically it's not just an addition sign. It is a circled addition sign. So this symbolizes your XOR. So your exclusive OR. So you have A plus B, okay, exclusive operator, and you have the logic diagram signal, okay, wherein your output is taken as X. So now let's see the truth table. If we give A also 0 and if we give B also 0, we get an output of what? 0. 0 plus 0 is what? 0. Then again, if we get 0 plus 1, we'll get 1. 1 plus 0 will get 1. And finally, for the last one, 1 plus 1 gives us basically 0. 1 plus 1 gives us basically 0. So what this symbolizes is, if you have 1 in the input and 1 in the output, if it was a normal addition, normal OR gate, it would give us 1. But here, if you're having both ones, it gives us a 0. It tells us that 1 plus 1 is, the other one is carry forward. Okay, the other one is carry forward. So that's why it is basically 0. You can just remember it in this way. OR gate, you will get 0, 1, 1, 1. For an XOR gate, if both are ones, you will get it here as 0. Okay, so this is your exclusive OR gate. Now, why the exclusive OR gate was developed? You all will be wondering this. This exclusive OR gate was developed for the addition operator. So has to add. So has to get a carry forward. Okay. So for that reason, this OR gate was XOR gate was developed. We will come to that in a later while. But as of now, XOR gate is understood till here.
Yes, sir.
Cool. Now, note the difference between XOR gate and OR gate. They differ in only one situation, as I told you. Your 1 and 1 gives you 1 in OR gate, and your 1 and 1 in an XOR gate gives you basically 0. And it is known as an exclusive OR. So you can see that EX. So that EXOR comes from there, which is even known as even XOR. Then we come for the NAND gate. Okay. Now NAND gate accepts two input signals as usual, the same. Boolean expression is X equals to A into B and a dash. You could even put a dash here, okay, instead of this, as I told you. This basically represents the inversion. So you could put a dash here on top of it. So X equals to A into B, the whole dash. Logic diagram is A into B, and you can see this small circle here. Okay, this represents the NOT gate. So that's the reason why we call it NAND. So it has the AND gate, okay, and it has the NOT gate as well. So the N represents the NOT and AND represents the AND gate. So you first have the AND gate. The AND gate will do the AND operation. That means A and B. Okay, so A into B, it would do the operation first. As you can see, A into B. So if A is 0 and B is 0, 0 into 0 gives us what? 0. But after that, this 0 enters this NOT gate. So this 0 gets converted to 1. So that's why you got your output here as 1. Everyone clear with this?
Yes,
Right?
sir.
Okay. Now, the second part, 0 into 1 gives us what? 0. Okay. And the output will give us what? 1. So 0 into 1 is 0. NOT gate makes it basically, oh god, I have an IP conflict. 1 minute. Huh? Guys, you all can hear me?
Yes, sir.
Sorry about that. As usual, the net went. So let's continue back again. I'll just share you my entire screen. Please let me know if you can see my screen.
Yes, sir.
Okay. Okay. So where we were, the NAND gate. So it could be A into B, the whole dash. Okay. So we get 0 into 1. If we have two inputs, 0 into 1 will be what? 0. But because of this NOT gate, that 0 will be turned to 1. In the same way, 1 into 0 is 0. But because of the NOT gate, that 0 will turn into 1. Then 1 into 1 is 1. But because of the NOT gate here, that 1 will become 0. So we have 1, 1, 1 and 0. Till here everyone is clear?
Yes, sir.
Now we have the NOR gate. The NOR gate accepts two input signals. Okay, if both are 0, the output is 1, otherwise the output is 0. Now you have your Boolean expression here. So in like how we had the NAND gate, we now have the NOR gate. So N and OR. N represents the NOR, OR represents the addition operator. So we have A plus B close bracket with the whole bar on top. So you can put one whole bar on top. So 0 plus 0 is 0. Okay. But here we have a NOT gate, so that 0 gets converted to 1. So we have the output as 1 here. Then again, we have 0 and 1. 0 plus 1 is what? 1. And the output of that is the inverse, so it will be 0. Then we have 1 plus 1 is 1. Okay, and the output of that is what? 0. So this is your NOR gate. Then review of gate processing. A NOT gate inverts its single input. Okay, so it is basically an inversion gate also they can call it. And an AND gate produces 1 if both input values are 1. So it only produces a 1 if all the input values are 1, otherwise it is 0. An OR gate produces 0 if both input values are 0. So it will only produce a 0 if both A and B are basically 0. Otherwise it will produce always 1. It is just the opposite of that of the AND gate. Then we have the XOR gate. XOR gate produces 0 if input values are the same. So that means if you have 1 and 1 for an XOR gate, what it will become? 1 and 1 gives us basically 0. For an OR gate, it would be what? 1 plus 1 is 1. But for an XOR, 1 plus 1 gives us a 0. A NAND gate produces 0 if both inputs are 1. Okay, a NAND gate produces 0 if both inputs are 1. A NOR gate produces a 1 if both inputs are 0. So as we saw in the truth table, we can see here for the NOR gate and the NAND gate. Okay, gates with more inputs. Now, as I told you, what we have seen here is only A and B, but there can be A, B, and C. Till now, the ICs which are developed in the electronic world, it is only A, B, and C, 3 input ICs. But you can combine the AND gates together, okay, to give you 4 inputs, 5 inputs, 6 inputs, whatever. So it doesn't matter. But the IC which is predefined are with 2 input and with 3 inputs, the dual inline package ICs. So gates with more than 2 inputs. Okay, so a 3 input AND gate would look like this. The Boolean expression would give us A into B into C. The logic diagram symbol would be A, B, C. So these are your 3 inputs and your output is X. So your truth table. So 0 into 0 into 0 would give us 0. 0 into 0 into 0 into 1 would give us 0, 0, 1, 0 would give us 0, and so on. And only 1 into 1 into 1 will give us 1. So this is for AND gate. As I told you earlier, you have to write your inputs A, B, and C, and your output is X. So always start off from the last, that is C, as 0, 1, 0, 1, 0, 1, 0, 1 continuous. Then again, in the multiples of 2. So 0, 0, 1, 1, 0, 0, 1, 1. So now here it will become 4. 0, 0, 0, 0, 1, 1, 1, 1. So this is how it you can write. So you will how many? So for basically 3 inputs, you will get how many outputs? 1, 2, 3, 4, 5, 6, 7, 8. So you will totally get 8 outputs for 3 inputs. In the same way, for 2 inputs, that is here, you will get how many outputs? 4 outputs. Now, constructing gates. Now, obviously, we came to know how a gate works. If you give 0 and 1 at the input of an AND gate, you will basically get 0. But obviously, how you're going to construct the gate, how internally you're going to make this gate so that it basically works. So these gates are basically combination of transistors. Okay, transistors are basically used to make these gates. So it could be a BJT, okay, it could be an NPN BJT, it could be a PNP BJT, whichever you want. Okay, so what transistors are used to basically make these gates, so as to get a 0 or to get a 1 as the output. Now, constructing gates. Now, if you can see, this is one transistor. Okay, okay. You have the emitter grounded. Okay, you have your base in the center, and your source is basically on top. So your base is basically, if you're going to give a high at the base, so you give a 1 at the base, the source and the emitter will be shorted. Okay, it will short the source and the emitter. Okay, and if you don't give a signal, the source and the emitter will be open circuited. Okay, the normal transistor operation. So let's see, if we give 5 volt at the base, or we give a 1 volt at the base, what will happen? The source, which is on top, will be shorted to the emitter. So if say the source was 5 volts, okay, and the emitter is, as you can see, it is grounded there, it is 0. And if the base is given 5 volts, then your source and emitter would be a short. That means there would be your source and emitter would be connected together. So this 5 volts which is there on the source would go to ground and it would short it. So if 5 volts is going to ground, what is your output signal? 0 volts. Till here everyone has got it? Guys?
Sir, can you explain that again?
Cool. You can see your base. Okay, I just want you all to interact with me, okay? You can remove your mics.
Yes, sir.
Okay, I mean, you can put on your mics. You have your base, you have your source, and you have your ground. Okay, now say if the source is connected to plus 5 volts. Okay, source is connected to what? Plus 5 volts. And your base is your signal to basically short the source to ground or not. Now, if the base is given 0 volts, okay, your source is not connected to your emitter. Okay, it is basically an open circuit. So what is the output here? What will be the output here? If your source is 5 volts, what would be the output? You can see one output is there. It would also be 5 volt.
volt.
Guys?
Yes, sir.
It would also be 5 volt.
5 volt.
Okay. If your base is now given, if your base was 0 volts, if 0 volts is there's no voltage given at your base, your source voltage of 5 volts, which has been given at the top, okay, your output would be also, if you are deriving the output from here, the output also would be 5 volt. But now say if we are giving, okay, a 1 volt signal at the base. Okay, now 1 volt is going at this base. When this 1 volt is going at the base, it is breaking this depletion region of the source and the emitter. Okay, and it is allowing the conduction from source to emitter. So if you're giving 1 volt at the base here, you're giving 1 volt at the base here, your source and emitter is shorting. Now source is how much? Source is constant now, it's 5 volts. Okay, so this
Yes.
5 volt will enter into this, and this 5 volt will go to ground. It is shorting. You got it?
Yes, sir.
Okay, so if you have, it's like basically you have a battery of 5 volts. Okay, and you're taking 2 terminals. Okay, both the terminals you're connecting with a wire, direct with a wire. What will happen? A spark will come, right? If you connect one tip of the wire on the positive of the battery and the other tip on the negative, what is happening? It is shorting the battery, right? Yes. So the voltage becomes 0. So when the base is given 1 volt here, what is the output here? What will be the output? Will the output be 0 or will the output be 5 if you're giving a 1 volt at the base?
0.
Correct. And if you're not giving a voltage at the base, what will be the output?
5.
Correct. You all understood this logic? Everyone? Okay?
Yes, sir.
Yes, sir.
Yeah. So your 5 volt, please don't switch off your mic. Keep your mic on. So if you all have anything, you all can just ask me. Don't
Yes,
worry. So when this okay, where I was, when this voltage is given here at the base, your source and emitter will short. So if your source shorts to your emitter, okay, all your voltage will be going to ground, and ground, as we know, is 0. If no one is there, who is there? God. Okay, here it is basically ground. Okay, so if no one is there, you have your ground, which is always there. All right, so all your voltage, okay, will be diverted towards your ground. Okay, a little bit of first year nostalgia, right? So okay, we'll come back. 1 minute, guys. Y'all can still see the screen, no?
Yes, sir.
Cool. Okay. Right. Now constructing gates. The earliest gates to create are NOT gate, NAND gate, and NOR gate. I think our lecture time has become. Professor Manjusha ma'am is calling me. Our lecture time has become, guys.
No, sir.
It's still on, right?
Yeah.
Okay. Then later I will see this. Anyways, constructing gates. The easiest gates to create are NOT, NAND, and NOR gates. Okay. So now we will construct the NOT gate, NAND gate, and NOR gate using these transistors. Now, if you see why we are using NAND gate and NOT gate to construct other gates, why we are not using the BJTs? These are basically transistors. Okay. Why we are using these transistors? Why we are not using the transistors to basically make AND gate and OR gate? Why we are mostly focusing on NAND and NOR? Can someone tell me? I had told this yesterday.
They are universal gates.
Correct. Because they are universal gates. And from the universal gates, we can basically make all the other gates. So that's the reason why we are focusing more on the NOT gate and the NAND gate in BJTs. Obviously, you can make your transistors, okay, and an OR also with your transistors as well. But we are basically focusing on the NOT and NAND because they are universal and they can be used to create all the other 6 gates, whatever we have. Okay, so the most basic and the most needed gates are your NOT gate, NAND gate, and your NOR gate. So first we'll see the NOT gate. The NOT gate, as I told you, is an inverse gate. Okay, so now we have here, as you all can see, we have a V input. Okay, we have a source and we have ground. Sorry. We have source and we have ground. Okay, and we have a V out here. Okay, now your V input, say if you're giving a input signal, as I told you, say if it is a 1 volt or a 5 volt, what will if it is a 1 volt given here, what will happen to the source and emitter? It will short.
Sure.
So your 5 volts will go to your ground and your V out will be what? 0. Okay, so we can see it is a inverse gate. Now your V input is nothing but your A. Okay, and your V out is your X. So if your input signal is a 1 here, if you're giving an input signal of 1, that is basically 1 volt or 5 volt, what will be your output? 0.
0.
Correct? If you're giving a V input of 0, these two things will not short. Your source and emitter will not short. So what you will get here?
1.
Correct. Okay. So this is how your inverse gate works using your transistor. Now to replicate a NAND gate. Which gate? NAND gate.
NAND.
Okay. So NAND gate, as I told you, it requires 2 and more inputs. So we have A and we have B. So we have V1 and we have V2 and we have your V out here. Okay. So your emitter is there, your source is there, V out, V1 and V2. Your V1 and V2 is basically your A and B. Everyone clear with this?
Yes, sir.
Okay, is basically your A and B. So V1 is A, V2 is B. So when we say it is A equals to 0 or we say V1 equals to 0, what it implies to is basically 0 volts or no voltage is given. Okay, and when we say A is 1, we assume some voltage is given. It could be 1 volt, it could be 5 volt. The standard is basically 5 volts. Okay, around 2.5 or 3 volt to 5 volt. That is basically taken as 1. Okay, and other one is 0. So now let's see the working of it, of a AND gate, how it works, NAND gate. Now for a NAND gate, 0 and 0 should give us what output?
0.
It's a NAND gate, N-A-N,
0.
0.
1. Okay,
Oh, okay.
so AND gate is what? 0 into 0 is 0, but it is AND.
Yeah.
A NOT operator is also there, so it becomes 1.
1.
So for 0 into 0 is 0, but because of the NAND operator, the NOT gate, it becomes a 1. So for 0, 0, you will get an output of 1.
1.
So let's see if this configuration of NAND gate is working. So I'm giving V1 0, I'm giving V2 also 0. Now if both are 0, okay, what is happening? What is the output?
1.
What is the output? 1,
1.
obviously. Because your V1 is 0. So obviously your source and your emitter of transistor 1 I have not shorted. They are opened only. And V2 is also not opened. It is open circuited. So you are getting 5 volts at the out. Guys, how much time more we have?
10 minutes.
10 minutes more, no? Meaning now it is, what time exactly?
10:05.
10:05. No, okay. Now I have to move out for the other person to come. Okay, I'll just complete this and then I'll move out. Okay.
Yes, sir.
So we have V1, we have V2. Okay. Now say V1 is 0 and V2 is 1. 1 means basically 5 volts. Okay. Just remember that 5 volts or 3 volts, whatever it is. Okay. Now if V1 is 1 here, is the source and emitter of the first transistor shorting? Or it is opening? Or is it open? If V1 is 0, this first transistor which is there on top, is it open or short? If 0 volt is there, will the source and collector short? No, no.
No.
It will be basically a open circuit.
Open circuit.
And if V2 is given 1, what will happen to the source and emitter? Here it will short.
Short.
Okay. But your 5 volts is on top. You can see source where it is written 5 volts is there. Is it shorted here? No, it is open. Okay. So the 5 volts on top will not reach the ground. Okay, because V1 has not opened. Okay, so what will be the output? The output will still be 1. You all got it? So
Yes, sir.
for a NAND gate, 0 into 1 gives us what? 0, but it is an inverse. Okay, so it has to give us 1.
1.
All right, you all understood the NAND gate?
Yes, sir.
Okay, in the same way how we have 0 and 1, same way you can put 1 and 0. Okay, and you'll get the same output as 1. Now, say V1 is 1 and V2 is 1. So what is happening? Both the source and emitter of transistor 1 and transistor 2 are shorted. So both are shorted right now. So what happens to the 5 volts on top? It is all diverted to the ground. So your V output becomes what? 0 volt. Everyone clear?
Yes, sir.
So 1 into 1 is 1, but since it's a NAND gate, N-A-N-D, not, that means your 1 into 1, which gives us 1, will become 1, 0. So that 1 will be converted to 0. And you're getting a 0 here. So this is how we can replicate using a transistor. In the same way, we have a NOR gate. Your source is on top, and now both the transistors are basically in parallel. Before it was in series. Remember that. Now it is in parallel. And your V output is taken on that parallel bar. Now you have your source and emitter for transistor 1 and transistor 2. So your V1, V2 is again your A and B. Now for a NOR gate, 0 and 0, A is 0, B is 0. What is your output? 0 plus 0, 0. But since it's a NOR gate, that 0 converts to
1.
1.
Okay. So 0, 0, 0 plus 0, the whole bar will give us basically 1. All right. So now let's see how we get 1. So say if 0 is at V1 and 0 is at V2, both are in open condition or short condition? Are they in open circuit condition or short condition? You all know what's open circuit and short circuit, right?
Yes, sir.
Yeah. So is the source and emitter open or short?
Open.
Correct. So if it is open, what will be the output? Come on, yeah. This is simple. What will
1.
be the output? 1, obviously. Okay. So for 0 and 0, 0 plus 0 is 0, but the whole bar makes it 1. Okay. So we got 1. Now, say for the condition of 0 and 1. Say for the condition of 0 and 1. Now, say V1 is 0 and V2 is 1. Say V1 is 0, what will happen? The transistor 1 is still open circuited. Okay. So your source and emitter is not shorting. But now for the V2, you are given a 1. So what happens to the source and emitter? It shorts, right? So if your source is shorting your emitter to the ground, and if your source voltage is 5, your 5 volts is diverted to the ground.
Ground.
So what is your V out?
0.
0.
0. Correct. Okay. So 0 plus 1 is what? 1. But it is an inversion because it's a NOR gate. So that will be basically 0.
0.
Till here, everyone understood?
Yes, sir.
Okay.
Yes,
I think I could go on the blackboard and show you this. Okay. But I think it's quite clear what I'm saying. Till here, you all got everything what I have done.
Yes, sir.
Yes,
Yes.
yes, sir.
Okay. And then you take for 1 and 1. Same thing. Got it now? If 1
Yes,
is
sir.
here as input and 1 is there at B as well. So if V1 is 1 and V2 is 1, Okay, what will happen? Both will short. Again, the output will be what? 0. So a NOR gate will be 1 plus 1 is 1, but the whole bar, that 1 becomes 0. So again, your output goes as 0. So this is how you can use transistors to drive or to make your NAND gate, NOR gate and NOT gates. In the same way, you can use transistors to even make AND gate and OR gates. Till here, everyone is clear?
Yes, sir.
Yes, sir.
So next class we'll go on the 18th slide, okay, which is circuits. All right. Okay. I will just take your attendance, guys. It's starting with I-1901, no? 01,
Yes, sir.
02, present, 02,
Present, sir.
03,
Present, sir.
04, 05,
Present, sir.
06,
Present, sir.
07,
Absent.
08,
Present.
09,
Present, sir.
10, absent 11.
Present, sir.
Okay. So roll number 1, roll number 7 and roll number 10 absent, right? Cool. Okay. Chalo guys.
10 is present.
Sorry.
Roll number 10 is present.
Roll number 10 is present. 1 minute. Okay. Done. All right. Chalo guys.
Thank you, sir.
Yeah. Most welcome.
Thank
Bye-bye.
you, sir.
Yeah. Okay. Thank you.